Hello physics students, this is Dr. Berenzi and this is lesson 7.2.2. In this lesson we're going to be able to identify the conditions necessary for any object to undergo simple harmonic motion and calculate the angular frequency of that motion. In order to do that, I want you to remind you of what we learned in 7.2.1, and that is when we had a mass on a spring, we had a force that is equal to some constant times the displacement of that spring. And it's negative, which means that it restores, the force wants to restore the equilibrium. In other words, if X is being pushed and displaced in a positive direction, this force wants to push back down to bring it back to equilibrium. And then we have Newton's second law, which states that force equals mass times acceleration. So if I replace this F with ma, and then I solve for a, I get a equals negative k over m times x. And then what we determined is that when this is true, the displacement x has to be a function of time, and that function of time x of t can either be a sine wave or it can be a cosine wave. And then we had some other things that we learned, like amplitude, angular frequency, this is time, of course, and then phase shift. And those we all learned in our last lesson, 7.2.1. Now, we learned that the angular frequency, which dictates how fast this object will move through its motion, is equal to the square root of k divided by m. And notice that I put this in red because I want you to see the connection between what angular frequency is and what is in front of our displacement x when we say a equals something times x, a constant. Well, this constant, the square root of it, ends up being our angular frequency, omega. So what other objects can exhibit simple harmonic motion? After all, we don't give this name to simply springs. We don't call it spring motion, we call it simple harmonic motion. Well, it turns out because there are a lot of other objects in the world that actually exhibit this very same behavior. Well, let's take, for example, a simple pendulum. In other words, we have a ball attached to a rod or a string of length L, and then we move it a certain displacement theta, angular displacement, and then we let this thing go, and it's going to start rocking back and forth, like this. Well, it turns out that you can show that for a simple pendulum, its tangential acceleration is equal to g times sine theta. And when I say tangential acceleration, remember, I mean talking about the acceleration of the motion around the circumference. Okay? The reason is because at this point, the direction of tangential acceleration is along a tangent line. So if I were to draw a tangent line, that would be the direction of our tangential acceleration. It turns out that when you can assume that theta is small, in other words, we don't lift this thing way up to 90 degrees. When theta is small, then you can actually show that sine theta can be approximated by just theta itself. And when I'm talking about theta, I don't mean theta in degrees. This has to be radians. So I better make sure that we all write that down. This has to be in radians. This approximation doesn't work for degrees. Radians, radians, radians. Okay, so when I replace sine of theta with theta, I get tangential acceleration is approximately equal. I don't know why I put equal to, but approximately equal. Ooh, that looks ugly. Let's just cross this out. and approximately equal to, so let's put our squiggly equal sign, is approximately equal to g times theta. Now, if you remember way back in Unit 5, we know that tangential acceleration is equal to alpha times the radius of the circle. Alpha is the angular acceleration. It's the acceleration of this angle theta. L is the radius of the circle, right? We have a string of length L or a rod of length L, and that is approximately equal to the g times theta. So when I solve for alpha, I get alpha is approximately, and I have to put approximately here, so alpha is approximately g over L times theta. Now, I haven't done a very good job keeping track of signs here, but I hope it makes sense to you that if theta is displaced in this direction, which is counterclockwise, that our tangential acceleration wants it to go the other way. So that tangential acceleration better be negative, which means angular acceleration is negative. So I better put a negative sign right down in here, which is what I just did. And likewise, you can imagine if the pendulum were displaced over here, well, that is a negative angle displacement, but it is going to want to bring it back to equilibrium, so it's the opposite of negative, which is positive. Well, this equation looks very similar to our spring equation. In our spring equation, we had acceleration A is equal to negative k over m times x. Now, instead of talking about linear acceleration and linear displacement, now I've changed it to angular acceleration and angular displacement. So I can actually use this, what I learned here, to set up an equation for what theta of t has to be. So theta as a function of time has to be a times sine of omega t plus phi. Or we could write a cosine omega t plus phi. Either one works. I just didn't put both of them right here. You could make a note right here, or cosine. That'll work just as well. Where now omega, our angular frequency, is equal to the square root of g divided by L. When we had a spring, omega was equal to the square root of this. Well, now we have this instead, so omega is equal to the square root of g divided by L. Now, take a look at this and just think about a pendulum. We have a length L. We have a gravity g. What else do we have that is usually a variable? Well, you're not going to have the same mass on here every time, are you? I mean, you could put a bigger mass, a smaller mass, very little mass, a huge amount of mass. The crazy thing is that this angular frequency doesn't depend on the mass. So no matter what mass I put on here, as long as I move it to this angular displacement, it is still going to show the same angular frequency. Actually, I can move it to a higher angle as long as theta remains small, and it's still going to have the same angular frequency, no matter what mass I put on there. That is really strange, isn't it? But that's how pendulums work. And as a matter of fact, it's really cool that that's the way pendulums work, because once people started realizing this, that this doesn't depend on the mass you put down here, you can use this to start keeping track of time. As long as you can measure this L accurately, and you can usually measure this L more accurately than you can measure this mass M. So that's why pendulums were such great timepieces way back in the day. I'm going to come back to this slide, but I want to skip it for now, because I want to go back to what I want to share with the advanced physics students as well. Nuts. Okay. So this will be the last slide for advanced physics. So there are other objects out there that exhibit simple harmonic motion. things like a guitar string. When you pluck a guitar string and you're pulling it back and then you're letting it go, just like you would a mass. And you can think of this, each of these sides as like a little spring in here under tension. And then when it tries to restore itself, it makes a sine wave. So you could actually, if you were trying to keep track of where the string is as a function of time, you would actually create a graph that looks like a sine wave. Or cosine wave, actually. It would start off, let's see, let me make a quick plot. It would start off down here at the very bottom, and then it would go up and down. So if you're trying to keep track of where the middle of that string is as a function of time, you're going to end up with a cosine looking graph. Another thing is a tuning fork. A tuning fork, you bang it against something, and then it starts moving back and forth. It starts moving back and forth like this. And if you were trying to plot where that position X is as a function of time, well, guess what you would get again? That's right, you would get a sine or a cosine wave. Okay, so there are lots of things that exhibit simple harmonic motion out there, and these are just a few of them. For those of you who are in advanced class, I really want you to understand the formulas for a pendulum, because you are going to be dealing with those. Other than that, you guys are done, but AP, I want you to stick around because we're going to cover a couple more slides here. So let's go back, AP. All right, and let's go to this one. So let's go back to our simple pendulum, and I actually want to show you how the math works out that proves that, let me back up here. I want to actually prove that this is true for a simple pendulum, okay? So I want to show you that this indeed is true. So what do I need to do in order to do that? Well, I need to draw a free body diagram. So I have force of gravity moving down. I have the tension force moving along a string. And that string makes an angle theta with respect to vertical. Now, I'm going to do something here that you may not have expected. You're probably expecting me to draw an X and Y axes that are vertical and horizontal. But I'm not going to do that. I am actually going to make my axes with respect to the radius of the circle. I don't know if you can even see that. That says radial. And then with respect to the tangent of the circle, so I call this tangential. So my axes are going to be radial in this direction and tangential in this direction. Now, it may not make sense to you why I do that right now, but you're going to find out in a moment why it becomes so convenient. So let's, first of all, that means that I have to break this down in terms of its radial component and its tangential component. So let's draw a right-hand triangle. And it turns out that the radial component is going to be mg cosine theta. The tangential component is going to be mg sine theta. Okay, well, after I have broken down all my forces, now I have to write F net equals ma for the radial direction. And that's going to be t minus mg cosine theta is equal to m times AC, which is the centripetal acceleration of our pendulum. Now, I'm not going to go any further with that one. I want to write down the tangential equations. Well, when I do the same thing for the tangential direction, I get F net equals ma, but a in that case is equal to tangential acceleration. So I get negative mg sine theta equals m times tangential acceleration. M's divide out, and I'm left, when I solve for a of t, I get a of t is equal to negative g times sine theta. Well, let's use my approximation. Well, actually, up to this point, then I've proved to you that really you do get a of t is equal to negative g times sine theta. I guess what I did before, when I prepared this, is I actually went ahead and did the approximation. So I'm going to approximate sine theta is approximately equal to theta. Now, I need to remember that tangential acceleration is equal to alpha times the radius of the circle. And the radius of the circle in this pendulum case is the length of my string or my rod. So now I have alpha times L is equal to, approximately equal to negative G times theta. And from there, alpha is equal to negative G over L times theta. And that means theta double prime is approximately equal to negative G over L times theta. I think at this point you have everything pretty much down. Again, this looks exactly like a spring. And so, whoops, I guess I was done. Okay. Well, let's go to the next slide. I want to show you one more. I want to show you the tuning fork now. Why is a tuning fork an example of simple harmonic motion? Well, the way that you usually get a tuning fork going is that you give it an impulse, and an impulse divided by whatever time it interacts with our table or whatever we strike it against is going to give us our force F. So we strike it on a table to give it a force F. And remember, this is a rigid object, so it has a stress placed on it, and that stress is equal to force divided by area. Now, what type of stress am I putting this under? This is a fixed point. This over here. I'm not pulling on it. I'm not pushing on it. I am actually creating a force perpendicular to this fixed point over here. And when you do that, you are actually creating a shear. So this actually is a shear stress. So when I take force divided by area, the area I want to consider is actually this little area on the very top of the fork right here. Well, my strain is equal to delta x divided by h. Well, delta x is how much this thing is moving up and down, right? It's vibrating, it's going up and down, like that. And h, remember, for shear strain, is this length right here. It is not the length along the displacement. So, I can set up my stress over strain is equal to my shear modulus S. So I need to know the shear modulus of the material. But let's solve this for stress. So let's say stress equals our modulus times strain. And then let's replace stress with force per unit area. So F divided by A is equal to, well, I'm getting a little out of hand there. Now I'll catch up here. So I replace stress with force divided by A, keep the modulus, and then replace strain with delta x divided by h. So I have force, solve for force, I have force equals our shear modulus times A over h times delta x. Well, that kind of looks a little familiar, doesn't it? Actually, I should have put a minus sign in front of here. You could imagine that if this thing moves up, that the force from the material itself is going to want it to come back to its original position. So there should be a negative sign in front of there. Now this is looking a lot like our spring equation, isn't it? Well, it does, and this thing right here, S times A over H, is equal to our omega squared. So when I strike this tuning fork, it is going to vibrate with an angular frequency equal to the square root of S times A over H. So it is, if I plot displacement versus time, delta x over t, I am going to get a sine wave, and that's exactly what you want with a tuning fork. You want a nice, clean sine wave, because that is what makes a perfect pitch. Okay, let's see what else I have here. I think I have one little thing. Oh yes, it turns out that you can actually, usually instead of dealing with angular frequency, when you're dealing with music, you deal with frequency. In other words, cycles per second. Or you deal with hertz. If you're familiar with a piano, the A below middle C is a sine wave that is equal to 440 hertz. So if I want to tune this fork to a certain note called A, I have to know what its frequency is. That note is 440 hertz, and then that's what I would put here. That's 440 hertz, and then I can figure out what my, well, I know I'm going to make it out of aluminum, so I know what that shear modulus is. But then I also know what dimensions I need to make it. I know what sort of area I need to make its cross-section. This little area here, I know what that has to be. And I know what this height h has to be. And usually what you do is you change this height h to get the fork to tune to different notes. So you create tuning forks with different lengths, and each of those lengths will correspond to a certain frequency, and that frequency corresponds to a pitch in a musical scale. And that's how tuning forks work. Alright, AP Physics, I hope you enjoyed watching the rest of this video and got a little more neat information. There are tons of things more than this that exhibit simple harmonic motion, but I didn't want to make this video any longer than it needed to be. But we'll keep working on this and find new applications for simple harmonic motion as we go along. Look forward to seeing you soon. Bye.